Thank you everyone for attending this talk, and good evening to you all. So, like Moslem mentioned, so today I will talk about from deterministic to distributionally robust integer programs. We will discuss about some cutting plane methods and decomposition methods. And it's interesting. So I have two connections with Sharif and Iran. So in the presentation, you will get to know some of my connections with both of these. So outline of this talk is as follows. So initially, I will spend some time to introduce integer programs and cutting planes. So I'm sure many of you might be familiar with integer programs. You might have studied in OR courses, but if not, we will touch base on basic definitions. And then we will also go through the basic definition of distributionally robust integer programs. Thereafter, we will get into presenting a consolidated cut generation procedure and its effectiveness both computationally and theoretically for solving production or transportation planning problems. I will also discuss some procedures to generate cutting planes for distributionally robust integer programs. And if time permits, we will also go through decomposition method for some distributionally robust integer programs. And finally, I will conclude my talk. So motto of this talk will be, I want to take the audience on a leisurely walk in my small garden so that each may pick for themselves a bunch of flowers of their liking. This is a modified quote from book by Hilbert on geometry and the imagination. So I've modified it a little bit for my sake. Okay, so let's get started with some basic definitions. Before we jump into definitions, let me just introduce this small problem in the supply chain. So here is a retailer who has a demand known over a planning horizon. This planning horizon could be a week or it could be a month. So essentially, retailer knows the demand for each day. And retailer has a truck which has a capacity of C1, which can be used to get the orders from a warehouse in each time period of the planning horizon. Now, the decision that retailer has to make is how much the retailer should order in each time period. And note that the cost for ordering also include a fixed cost to hire this truck as well. And the objective is to minimize the overall ordering cost and the holding cost. If you see this problem in manufacturing settings, so essentially a truck will be replaced by a machine and fixed ordering cost will be replaced by typical setup cost. And this problem can essentially be defined as a network flow problem. So here is a special case of a network flow problem where each node is representing a day. And for a day P, let's say for a day P, we have to decide what should be the inventory at the beginning of day P, which is SP minus 1. What should be how much is to be produced on day P, which is XP. What should be the inventory at the end of day P, which is SP, given the demand, which is DP. And also we know some of the cost per unit cost of production, per unit cost for the inventory. And we also have a fixed cost, which means that if a machine is set up on day P, then there is a fixed cost of F1P that is to be paid. And if machine is not set up, then there is no fixed cost. So so just to get the understanding of the audience, so how many of you have seen this type of problem before? Can you raise your hand? Like you can see it through the virtual. Great. So I'm seeing some folks, they have raised their hand. So what I will do is I will briefly describe this formulation. So in order to formulate this problem, essentially we need some set of constraints. And these are our decision variables, which is how much to produce and what should be the inventory at the beginning of each day and at the end of each day. And since we know the cost and we want to minimize the cost, so our objective function is to minimize the total production cost or total inventory cost, and the amount or the fixed cost that is to be paid. For the constraint, we will have a flow balance constraint. So this constraint is essentially saying the input to this node is equal to the output of through this node. So the flow in is equal to flow out. So I get SP minus 1 plus XP is equal to DP plus SP. And since we have a fixed cost, so we associate a binary variable Z1P, which is if I'm going to set up a machine on day P, then this Z1P will be having a value of 1, so which means that the production in that time period will have a bound or upper bound of C1. And in case I decide not to produce on day P, then Z1P will be equal to 0, which will force XP to be equal to 0, so which means that there is no production on that day. Okay. And my XP, which is the production, and the inventory variables are greater than equal to 0. And Z1P is my binary variable. So this is a typical constant capacitated lot sizing problem because I have one truck in each time period. Now, this problem can be extended to the what we refer to as a multi-module capacitated lot sizing problem. So the setup is all same, except that now retailer has more choices. So there are, let's say, n different trucks of different capacities, C1, C2, so on to Cn. And the retailer can use any subset of these trucks to order the material in that particular time period. Same thing with the setup in the machines. So you have machines of different capacities, and you can get and you have to select a subset of those machines that are to be procured for that time period or to use for that time period. But there is a fixed cost corresponding to each of them. So pretty much the framework or the formulation will remain same, except that now we will have, instead of having Z1P, we have ZJP as a binary variable corresponding to each truck or each machine. So which means that if I'm going to pick truck J or machine J in period P, then ZJP will be 1, otherwise it will be 0. This helps us to, so the modification will be that the production capacity in each time period is essentially a binary is the sum of the binary multiples of the capacities. So let's say if I have only 2 trucks of capacity C1 and C2, then the production capacity is C1 plus C2, but I can order either C1 capacity truck or C2 capacity truck or C1 plus C2. Okay, so this is, we refer to it as multi-module capacitated lot sizing problem, abbreviated as MCLS. So essentially, this is just an example of a mixed integer program where you're minimizing a linear function subject to some linear constraints, and some of the variables are continuous and some variables are integer or binary in this case. So binary is a special case here. So this class of problem is referred to as mixed integer linear programs. And varieties of problems ranging from production planning, facility location, network design, healthcare planning, even in aviation industry, and also for social issues, various problems that arise in these domains are being formulated as mixed integer linear programs. So this is all about the basic definition. Now let's get more into more mathematical, formal definition of a mixed integer linear program. So here is a linear program, which is you want to minimize a linear function subject to some linear constraints, and all the variables are continuous. So geometrically, if I observe, essentially this red region is, let's say for this example, with x1 and x2 as a continuous variable, this red region is my feasible region, and I know that optimal solution will be at one of these extreme points. Now, if I make the problem, or if I want that these x1 and x2 can only be integer, then I get this integer linear program where, again, I'm minimizing the linear function subject to some linear constraints, except that my decision variables are now integers. As a result, my set of feasible solutions is, instead of that shaded red region, now it's these red dots. And integer programs, or IP, are NP hard in general because given a formulation, I only know about these black boundaries corresponding to the it's LP relaxation, which is if I relax the integrality restrictions on this problem. And I do not know about all of these red boundaries, which are essentially providing me the convex hull of the integer solutions. So therefore, it is crucial for us to develop some cutting planes or inequalities. So in this case, this is this line, which is creating this half space below this region, uh, so that I can reduce the gap between this LP relaxed region and these red boundaries. And these inequalities are sometimes referred to as valid inequalities because we don't want any of the integer points to be cut off. And they are also referred to as in shortcuts. So I will be using them as calling them as cuts because they cut off this LP relaxed region. And the strongest one could be referred to as facets, which are the cuts or the hyperplanes corresponding to these red boundaries here. So if I can add these red boundaries, so I am able to obtain some information about uh, the convex hull of the integer solutions. And these cutting planes can also be used within a branch and bound framework, where at each node we can add these cuts to get a better approximations of the problem and get a better lower bound as well. So in this talk, in the part 2 of this talk, I will discuss about how to generate these cuts, and I will share a method or a cut generation procedure uh, for general mixed integer programs. And I've been saying mixed integer program. So essentially, mixed integer programs are just another integer programs where, in addition to integer variables, you also have some continuous variable. And I will use the term LP relaxation or linear programming relaxation of a mixed integer program, denoted by MIP, when I relax all the integrality restrictions on all integer variables. Okay, so this is a mixed integer linear program. But before we move to part 2, let's also have go through the definition of distributionally robust integer programs, and thereafter we'll get more into the technical details of new methods to solving these problems. So what is a distributionally robust mixed integer programs? Let's go back to the example we were discussing. We were discussing about this multi-module capacitated lot sizing problem. And here, when we were planning for the retailer, essentially we were assuming that the demand is known for all the time periods in the planning horizon. But what if the demand is not known for all the time periods? Essentially, or let's say I know the demand for the initial k time periods from D1, D2, so on to dk is known. But for all the time periods after k, from k plus 1 to say m, I do not have the complete information of the demand. It's not that I have no information about the demand. Based on my historical data as a retailer, I have stored, I have some idea that the demand could be various different possibilities. So let's say say there is a possibility of high demand, there is a possibility of medium demand, there's a possibility of low demand. And there's a probability corresponding to that. Uh, so I will refer to one possibility as a scenario or a realization, and the probability corresponding to that is P1. Similarly, there is another scenario for the probability corresponding to that is P2, and there's a scenario 3 where is a probability corresponding to that is P3. And there can be thousands of such scenarios. So this is just a toy example. So in that case, how should a retailer plan things ahead of time so that when the uncertainty will be realized, the retailer is still able to minimize the expected cost? And I will go through what exactly I mean by the expected cost in a minute. So that's the setup we are looking for. And here, if I assume that these probabilities are known, then that falls into the category of stochastic uh, problems. But if I assume that I actually don't have the complete information about the probabilities as well, then that belongs to the domain of distributionally robust optimization. So more formally, so we went through this deterministic linear program, and when we saw the definition, we realized that all the cost coefficients and uh, the data parameters and the constraints are assumed to be known, and that's why it is referred to as a deterministic linear program. But what if some of these data parameters, let's say some of the parameters in this vector G, matrix E, W, or this vector R are not known. Or we know that there is an uncertain data, and the data corresponding to this, to these vector and the matrices, is described by a random variable CP, which is of the size of the total number of elements in these vector and the matrices, which follows, in this random variable, follows a known probability distribution P defined over a sample space big omega. So that type of a problem is referred to as stochastic linear program. Now, what does it mean by two-stage? So two stages, here we are having two stages of decision making, like we saw in the previous example. So the idea is we have to decide what should be the inventory and the production plan for the initial K time periods, and then when the uncertainty is realized, we have to decide what should be the inventory and the production after K time periods. Another example could be, let's say I have to procure chair and I have to manufacture chair and tables. And in order to manufacture chair and table, I have to procure different types of raw material. If I know the demand for the chair and table, then I can procure my raw material just by designing a linear program or an integer program and can solve the problem. But what if I do not have the complete information about the demand or the exact information about the demand, but I have to procure my raw material today, and the production will be done a week from now based on whatever is the demand that will be realized. And I have some information, which is I have high demand, I might have low demand, or I have medium demand. So I could be very conservative or risk averse to say, okay, let's go with the low demand. So in that case, since there is a possibility of medium and high demand as well, and I have procured my raw material right now, so I cannot produce more than that. So I might not be able to make as much profit as I wanted to do. Or I could be uh, more risk taking, which is I can say, let's procure the raw material based on the high demand. Again, there's a possibility of medium and the low demand as well. So I may end up having excessive inventory as well. So how should I decide my decision, which is how much to procure, referred to as here and now decision variable, that I have to decide now, so that my wait and see decision, the decision that will be made after the realization or the observation of the uncertainty, uh, can be made effectively. So I have stage one where I am making decision X. Once I observe the uncertainty, we have the stage two where the decisions are being made corresponding to each data scenario. So here omega denotes the specific data scenario which belongs to this sample space big omega. Okay, so this problem is not new. This is it goes back to 1955 when Denzing provided this linear programming reformulation for a problem where this probability distribution is defined over a finite sample space. So you have this problem. So essentially, uh, G omega, T omega, W omega, R omega are representing one possible realization of the random vector. And he introduced these y omega variables corresponding to each scenario, thereby leading to this large scale problem because you have these constraints corresponding to each scenario and these y omega variables corresponding to each scenario. Interestingly, this problem has a nice block angular structure, which is if you observe, you have this x, but this y omega, so the coefficients of y omega are not repeating in the sense that if you go from scenario omega 1 to omega 2, so you have a separate block corresponding to that, which helps us uh, to decompose this problem. And essentially, same thing can be said about the two-stage stochastic mixed integer program. So the only thing that I have done is I have now allowed some of the variables to be integer. So we can use typical Bender's decomposition setup uh, to define this problem where you want to minimize. This is your first state problem where you want to minimize Cx plus the expected value of this function referred to as recourse function. And essentially this function, this q omega x, is dependent on a scenario omega. And it's another mixed integer program where the constraints are dependent on x. So as x will change, these constraints will change. So we can refer to as a parametric mixed integer program. Now, one of the issue with this is now you have an integer program, and if we try to solve this problem using uh, the typical methods, then it is much more challenging because integer program by itself are hard. So for each x and for each omega, I have to solve this problem again and again. Now, so this is stochastic mixed integer programs where I'm assuming that the probability distribution is known. So there is a new framework which is referred to as distributionally robust optimization, which is kind of a hybrid of stochastic optimization and robust optimization. So in stochastic programming, even if it is not two-stage setup, the uncertain parameter follows a known probability distribution, and objective function is specified by taking expectation over these parameters. In robust optimization, essentially we handle uncertainty by solving this min-max problem because the max is taken over a set of possible values of uncertain parameters. Essentially, we are looking for a worst case scenario. Robust optimization is more like a hybrid of these two approaches, where instead of taking the worst case scenario, you're looking for a worst case probability distribution. So the understanding is, and it goes back to Scarf in 1958 when he introduced this concept of distributionally robust optimization. I think back then it was more referred to as min-max stochastic program. So DRO terminology is new. So in this setup, the idea is that I do not have the complete information about the probability distribution. But based on my data, I can evaluate that the probability that I'm looking for, I know the mean or the variance for that probability, for example. So this, I'm looking for a set of all probability distributions that will have that mean and that variance. Or I know the bounds on the means and the variance. So I know I'm looking for a set of all probability distributions, which is denoted by this fractured P. And the objective is to optimize this expected value of the objective function for the worst case probability distribution. Okay, so the expectation is coming from stochastic, and the min-max framework is coming from robust optimization. So this aspect can be combined with two-stage stochastic mixed integer programs, thereby leading to two-stage distributionally robust mixed integer programs. Where in the first stage, we have this Cx plus, we are maximizing this expectation where the max is done over the set of over this set of distributions referred to as ambiguity set. And again, in the setting that I will discuss, we will assume that we have the finite sample space. Some of the significance of this framework is it allows incomplete information of the probability distribution. It also provides some sensitivity analysis. So let's say I have a reference distribution and I'm looking for how a deviation in my probability distribution can impact my solution. So that could be another framework where this can be used. Also, it allows adjustable level of risk aversion. So if I assume that this fractured set P is a singleton set, which means it has only one probability distribution, then it reduces to two-stage stochastic problem. If I assume that this ambiguity set is essentially set of all distributions defined over the sample space, then this will reduce to robust optimization because that will include distributions corresponding to each scenario as well, which means that only that particular scenario will happen. So by adjusting this ambiguity set, I can adjust from risk neutral, which is stochastic framework, to most conservative, which is robust optimization. Okay. Any questions so far? So we have the setup is there. Now we will be getting more into the details of any question so far? Okay, awesome. So let's discuss about some cutting planes for mixed integer programs. So like we discussed before, so cutting planes are important, but how to develop these cutting planes for mixed integer program? So here is a mixed integer program where we have uh, two set of decisions. One is x, which are all non-negative integer variables. and we have z, which are non-negative continuous variable. And we have a set of constraints, ax plus ez greater than equal to r. So one approach is we can form a relaxation by aggregation and then create cuts for that. Okay. Uh, so which means what I can do is I can aggregate all the constraints in as a single constraint. I'm just going to add them up to get a single constraint set. And this is the set that I will obtain. I refer to as a single constraint relaxation. Uh, and or what I can do is I can pick or multiple subsets of these constraints and aggregate all the constraints in each of those subsets to get this multi-constraint relaxation. Now notice that any point or any solution that will satisfy these constraints will also satisfy the constraint, the single constraint, or the multi-constraint relaxation. And essentially that's why the original feasible set is a subset of the feasible set of the relaxation. So the original feasible region is within the feasible set of the relaxed problem. So therefore, a valid inequality or a cut for the relaxation is also valid for the original problem. By valid, like I mentioned before, it is not cutting off any feasible solution. But how to generate these cuts? So there are various different procedures. So mixed integer rounding, or MIR, is a well-known cut generation procedure, and it is developed as follows. So instead of looking at the general mixed integer program, so here you are looking at this simple mixed integer set, which has only one unrestricted integer variable y, one non-negative continuous variable s, and only one constraint alpha 1 y s greater than equal to beta. Okay. Interestingly, this and later on we will see how this procedure can be used to generate cuts for the general mixed integer programs. So interestingly, I can graphically represent it, right? And if I try to do that, let's say y is on this axis and s is on this axis. Y are integral and s are continuous. So all these blue lines is essentially representing my feasible region. And this is the hyperplane corresponding alpha 1 y plus s equal to beta. So the intercepts that I have are beta and this beta by alpha 1. Very, very basic high school math, right? If I take the LP relaxation of this set, which means if I remove the integrality restriction on y, I will get this gray region. It's not bounded, it's like it's extending, but it's this gray region that I have. Now, I'm interested in the convex hull of this mixed integer set. So can I say that the LP relaxed region is giving me the convex hull? No, because something is missing here. So I'm missing this part, right? So I need one more inequality corresponding to these 2 points, because otherwise I'm getting this extreme point, which is beta by alpha 1. Assuming beta by alpha 1 is not integral, this is can be fractional as well. So in order to derive this inequality, or in this case, this line passing through these 2 points, I can use very simple high school math. I can say, okay, let me compute these 2 points. So what will be this point? So this point is ceiling of beta by alpha 1, or round up, because I'm interested in the integer value. And this point, since the y component here is floor of beta by alpha 1, so I can substitute y up here and can get the value of s. So s will be beta minus alpha 1 times floor of beta by alpha 1. So knowing these 2 points, I can very easily compute the equation of this line, which is as follows. And essentially, this is referred to as a mixed integer rounding passage. Okay, so this is there, but now how it is being used to develop cutting planes for the general mixed integer programs. So let's look at this single constraint relaxation. So if you recall, what we did was we had x were our integer non-negative integer variables, and zj are our non-negative continuous variables. So we aggregated all these constraints and got this single constraint up here. Now what we can do is we can play around with this these inequalities. So this is the original inequality. Now I will replace this E hat J with max of E hat J and 0. If I do that, then this is greater than equal to the previous expression. And then I'm going to split this set 1 to N1 into two sets J0 and J1, so that I'm not doing any modification. I'm just splitting them into two different sets. For all the uh, for all the j in J0, I will replace this A hat J with alpha 1 times ceiling of A hat J by alpha 1. Note that since xj is non-negative, and uh, and here I'm replacing alpha hat j with a coefficient which is greater than a hat j, then this is greater than equal to this expression up here. And at the same time, I will replace this a hat j. I'm going to write it in terms of alpha 1 times ceiling of a hat j by alpha 1 uh, plus this remainder, which is the leftover. Okay, so I'm just rewriting this a hat j in this term. So like alpha 1 could be any arbitrary number I have picked, and I'm just writing it in terms of the remainder and alpha 1 times the integer I have, value that I have. So I'm still getting, so all I'm doing is I'm getting valid inequalities for the set. Now what I'm going to do is, as you can observe, I'm going to collect these terms corresponding to alpha 1. So this was the inequality I had. I will collect all the terms corresponding to alpha 1. So this is, and now notice that this is just an integer expression because all the coefficients are integer, all the variables are integer. And the remaining part up here is a non-negative continuous expression here. So I can just substitute y equal to this integer expression, s equal to this non-negative continuous expression. And since I already know how to obtain uh, a valid inequality or a facet for this simple mixed integer set, I can just substitute the value of y and s and replace beta by b, and can get this well-known mixed integer rounding cut developed by Nemhauser and Woolsey back in 1990 for this single constraint problem. And essentially, this will be a valid inequality for the original problem as well. So in this case, if I set alpha 1 equal to 1, I will get Gomri mixed integer cut. So one of the interesting aspect of using this framework of studying simple mixed integer set is that this mixed integer rounding inequality derived from this process for different problems like lot sizing, facility location problem, and network design problem essentially subsume various other inequalities that were derived independently for these problems in the literature. So MIR came in like 1990, right? So there were various inequalities that were derived in the literature separately for these problems, and later on it was realized that we can derive those inequalities just by applying the mixed integer rounding procedure. So the idea is, uh, can we generalize this mixed integer rounding procedure? One way to consider is, okay, why not to consider some multi-constraint sets which has multiple integer variables? So here is this set which I refer to as continuous multimixing set, and the procedure corresponding to that is referred to as continuous multimixing cut generation procedure. So this is a set which has m constraints, where each constraint has n integer variables, n different integer variables, a continuous variable vi, a non-negative continuous variable vi, and a continuous variable s, which is common among all these constraints. I denote this set by qmn, where m denotes the number of constraints and n denotes the number of integer variables in each constraint. If I set n equal to 1 and m equal to 1, I'm essentially going back to the simple mixed integer set that we saw in the previous slides. So over the time period, various extensions of the set Q11 has been considered in the literature. The closest one is this continuous mixing set by Van Weeve in 2005, which discuss about QM1, which has m constraint and one integer variable in each constraint. And essentially, if we can study the inequalities for this particular set, then the various inequalities developed in the literature for these problems can also be developed uh, by the continuous multimixing procedure. So what we will assume is, let's say some of these coefficients, they satisfy so-called n-step MIR conditions, and I will show what are those conditions in a minute. And essentially, these sets appear in as a substructure in problems such as multi-module capacitated lot sizing, facility location, and network design problem. Later on, we will see for the lot sizing problem how it works. And this work is, so this is my first connection with Sharif. So this was done with my PhD advisor, Dr. Kevash Kianfer, who did his undergrad and master's from Sharif. So this is my first connection with Sharif, and so essentially, uh, uh, yeah. So so these MIR inequalities are, I'm not getting into the details. So these are some conditions, but if alpha 1, alpha 2, and alpha n are divisible, then these conditions are automatically satisfied. So I won't get into the details of what are these conditions, but I would like to introduce this notation that I will be using, which is beta superscript p. So if I'm representing beta superscript 1, then essentially it is equal to remainder of beta with respect to alpha 1. So that's why I have beta superscript 1 is equal to beta minus alpha 1 times floor of beta by alpha 1. If I'm writing beta superscript 2, then that's remainder of beta superscript 1 with respect to alpha 2. And so on. If I'm writing beta superscript n with respect to alpha n, beta superscript n, then it is remainder of beta superscript n minus 1 with respect to alpha n, and so on. So you will see some of these notations. All right. So in order to derive inequalities for this set, like I mentioned, so for the set where n is equal to 1 has been studied by Van Weave. So we are extending the results and presented in that paper. So what is being done here is, so we consider this complete directed graph G, which has m plus 1 nodes, where node 0 corresponds to s greater than equal to 0, and node I corresponds to constraint I in set QMN. Okay, so corresponding to each constraint in this set, we have a node in this graph. And we associate a linear function psi n prime ij with this arc ij, and these are defined in this form. So this is a more compact form, and it's a linear function. It's a compact form because you have this psi, which is an integer function, and this beta, this remainder or the recursive remainder function here. So let's not get into the details of like how this function is being defined, but let's say I have this linear function associated with each of the arc in that graph. So our first result is that we can derive some inequalities as follows, referred to as n prime step cycle inequality. So given an elementary cycle C, n prime step cycle inequality associated to that cycle C is essentially, I will aggregate or the sum all the linear functions corresponding to arc ij in that cycle C, and aggregate this and set it equal greater than equal to 0. And this is referred to as n prime step cycle inequality. So we prove that these inequalities are valid and they define facets for the convex hull of the set QMN under certain conditions. Interesting thing is, like you might have seen, I mentioned that these are consolidated cut generation procedure because QMN generalizes various simple mixed integer sets studied in the literature, and as a result, this class of inequality subsume mixed integer rounding inequality, mixed MIR inequality, cycle inequality, n-step MIR inequality, and mixed n-step MIR inequalities. So here is this one toy example. So if you consider continuous two mixing set with two rows or Q32 which means that there are three constraints in the set, and each constraint has two integer variables. And there is a continuous variable v1, v2, v3 corresponding to each constraint, and there is a continuous variable s which is connected, which is common among all the constraints. And I want to derive an or a class of inequalities for this particular set. So the process will be, I will generate a complete directed graph G with 3 plus 1 with 4 nodes. And I will be writing this linear functions corresponding to each of the arc in this graph. And there it was looking a little bit more sophisticated, but essentially these are nice linear functions in terms of the variables of the set. And once I have all this linear functions, in order to derive inequalities for the original set, all I have to do is I have to pick a cycle. So let's say I pick a cycle which is 0, 3, going from node 0 to 3, 3 to 2, 2 to 1, and 1 to 0. So it's an elementary cycle. And all I'm doing is I'm aggregating the linear functions corresponding to each arc in that cycle and setting this greater than equal to 0. And that will give me a valid inequality for the original set. Okay, so depending on which cycle I'm going to pick, I will get different inequalities for the set. So in while explaining QMN, I mentioned that the coefficients have to satisfy the so-called n-step MIR conditions. So we have thereafter, after that paper, we further extended our results for the case where no conditions are imposed on them. And we provided some facet-defining extensions of n-step cycle inequalities in this paper. Furthermore, we considered the case set where you have multiple constraints, but also you have bounds on the integer variables as well. And develop this new class of inequalities referred to as mingled n-step cycle inequalities. And again, I won't be getting into the details up here, but these inequalities, they kind of generalize or subsume, because it's a bigger class of inequalities, subsume various inequalities in the literature, like continuous cover inequality, cover and pack inequalities, mingling inequalities, n-step mingling inequalities, and n-step cycle inequalities that we discussed before. So how to use these inequalities to derive cutting planes for multi-module capacitated lot sizing problem that we saw at the very beginning. So here is the formulation that we had. What we are going to do is we are going to use the same procedure, which is we will aggregate some of the flow balance constraints. So these equality constraints, we are going to add them up. Let's say I'm going to add the constraints from time period K to some mi minus 1. Like, let's not get into the details, but let's say I'm aggregating them up. So I will get this sk minus 1 plus some of these xp for p from k to mi minus 1 equal to sum of the demand from time period k to mi minus 1 plus this smi minus 1. Okay, now since this smi minus 1 is greater than equal to 0, because it's the inventory, I can just replace it with this inequality. Okay, now once I have this inequality, I can relax some of the these continuous variable xp by using their upper bounds. So let's say for p in set si, I'm going to relax them by using this constraint. So for p in si, I'm removing those xp's and I'm just replacing them with their upper bound here, which is obtained from this constraint here. So I get this valid inequality for the MCLS problem. Interestingly, if you observe, as if I fix k and I'm going to change this mi minus 1, I'm going to get this set which is of the form where this sk minus 1 can be considered as s, and this is represented as a non-negative continuous variable corresponding to that constraint vi. And here I have this sum of alpha t yit greater than equal to beta I. So which means that if I can derive an inequality for this continuous multimixing set and replace the s by sk minus 1, vi by this expression, and yit by this expression, and beta by the sum of this demand, I will get a valid inequality for this multi-module capacitated lot sizing problem as well. So we conducted some of the computational experiments where we randomly generated some of these instances, and we also had this separation algorithm. So essentially, at the root node, so we compared our results with the Cplex. So in Cplex, at the root node, we add some of these inequalities using a heuristic, and once we had added those inequalities, so since these inequalities reduce the gap by 82%, uh, we just let them be there and then ask C+ to solve the rest of the problem. Okay, so when we do that, in comparison to the C+ with its default setting, so the number of nodes needed is reduced by 8.4 times, and the total time, which includes the current generation time, is reduced by 8.9 times on average. So that showcases that these are computationally strong inequalities. But one of the things that is to notice is, so far when I'm saying that we have developed these inequalities, these are only valid inequalities. So, so thereafter I studied what could be the facet defining properties. Can these inequalities, we observe that empirically they are strong, but are they strong theoretically as well? So so I studied some of these conditions under which the inequalities or the some special cases of the n-step cycle inequalities are facet defining for the lot sizing problem. And various inequalities known in the literature are the special cases of it. So I looked at those classes. So we looked at, so in this paper, we looked at the conditions under which the KLSI inequalities of Pushy and Woolsey are facet defining for the problem with problem with single module, but with batches, which means that you don't have Z is not just the binary variable, but also an integer variable. Similarly, we looked at the facet defining properties of mixed KLSI inequality and sequential paired inequalities derived by the sequential pairing procedure of Guan and others. And we also looked at the multi-module capacitated lot sizing problem and looked at this n-step mixed KLSI inequalities and derived sufficient conditions under which these inequalities are facet defining for the multi-module lot sizing problem. One more open question I realized while working on this paper was, we know that when we are dealing with single module or the constant capacitated lot sizing problem, those problems are polynomially solvable. What about multi-module capacitated lot sizing problem? If I set n equal to 2, or if I set n equal to 3, will the problem be still polynomially solvable or not? I still have NT number of binary variables. So what can we say about that? So I raised this question to one of my PhD students, and we started working on that aspect in terms of, can we demonstrate the existence of polynomial time algorithm for multi-module capacitated lot sizing problem with fixed n. So, and plus we looked at some more extensions, which is we considered MCLS with subcontracting. And in literature for single capacitated or constant capacitated problem with subcontracting, Artemtuk and Hogbaum has derived an algorithm that takes order of OT5. So we started looking at how can we solve this problem using a dynamic programming approach. One way we realized is we can reformulate these problems into uncapacitated lot sizing problem with piecewise linear or concave production cost. But the number of the breakpoints that will be needed for this function will be exponential, which is 2 to the power n minus 1. And essentially, if we do that and use, so we developed a new algorithm for this problem as well, and use this algorithm to solve the problem, then it takes t to the power 2m plus 3, which means that if I'm considering n equal to 10, the number of breakpoints will be 1023. The complexity of the algorithm by this reformulation will be t to the power 2049, which was huge. So we said, can we develop something better than that? So my student, he was able to come up with an algorithm which was for n equal to 1 has the same complexity as in the literature, but as you increase n, the overall complexity of the algorithm is now t to the power 2n plus 3. But this addresses the question that for a fixed n, the multi-module capacitor lot sizing problem can be solved in the polynomial time. Okay, so this was about deterministic setup. Before we go into this world of uncertainty, any questions so far? I'll just pick up the button. Okay, so there are two frameworks that I will be discussing under in this part of the presentation. One is how to use cutting planes, and we will see. I don't think I will be having enough time to discuss about decomposition methods, uh, but I will quickly scan through that, like the framework of it. So we know that integer programs can be challenging to solve. Now, when we bring these integer programs in the stochastic framework, or even in the distribution robust framework, they are more challenging because if you know about approaches to solve two-stage stochastic mixed integer programs, what you have to do is you have to compute this q omega x for each omega and x, and which makes it a little bit challenging because I have to solve this integer program again and again in my algorithm, and I can have thousands of scenarios, and x, the set of feasible solution, can also be large. So the question that came was, can we obtain tight formulations or linear programming equivalent for the second stage subproblem by adding so-called globally valid cuts? Okay, because again, I can solve this problem for a given. If you give me x, this is a mixed integer program, so I can solve this by using cutting plane approach. But the issue is, as I'm going to change x, the feasible region is going to change. So the cuts that are developed for a given x might not be valid for another x. So we are looking for globally valid cuts, which means that irrespective of what is x, we the cuts that are being added will be valid irrespective of x. Okay, that's what I mean by globally valid cut. So it's the framework of uh, referred to as second stage convexification approach. If we can do that, so essentially we will be able to reduce the number of integer variables. So if we look at the extensive formulation, in the extensive formulation, we will be able to reduce the number of integer variables from 300,031 to 31, because I mean it's pretty much. So here I'm saying that I'm considering 10,000 scenarios, and each scenario has 30 integer variables. So all of those variables are gone. Or if I'm considering 1,000, yeah, I'm considering 1,000 scenarios, and each has the remaining 300 integer variables. That's one aspect. Other thing is this function q omega x, when y omega is continuous, is a nice piecewise linear convex function. But the presence of integer variable is making it a lower semi-continuous, non-convex, discontinuous function. As a result, if I can obtain a linear programming equivalent, we can obtain a nice convex function in X. So this work started with the assumption of knowing for the case when we know the probability distribution, and that's why I'm referring to it as two-stage stochastic mixed integer programs, and with finite sample space, that the number of scenarios are finite. So in this setting, various algorithms have been known in the literature for different frameworks, starting from Laporte and Lowash, depending on whether you are considering binary or mixed integer or integer variables in the first and second stage. So we said, let's look at some of the structured problems in the second stage and see what can we convexify the second stage problems. So here is this one example of the convexifiable second stage problem. So you have this recourse, this second stage problem, where so you have the set of variables is y1 omega, y2 omega, and y3 omega, where y1 omega are integer variables, y2 omega are a non-negative continuous variable, and y3 omega are uh, is a single very continuous variable which is appearing in all the constraints. And now you can see the connection between this set and the continuous multimixing set. So we observe that if this matrix W omega is unimodular matrix, then by adding some order of m square linear constraints and order of m continuous variable is sufficient to relax the integrality constraints on y1 omega variable. And this relaxation it's not just a relaxation, it's a linear programming equivalent of the original problem. So which means we are not losing the integrality of y1 omega variables. And like I mentioned, so this set has some interesting relationship with the continuous multimixing set, except that here we still have this t omega x, which was not there in that set. So if you're interested in more such sets, you can refer to this paper. We have various other sets considered here, and that motivated us to consider this idea of second stage convexification and take it to two-stage stochastic nonlinear programs as well. So here is a two-stage stochastic conic integer program. So only thing that I'm doing here is I'm adding in the second stage, I'm also introducing this LP norm in the objective function, where LP norm is the usual definition of LP norm. And conic programs, it can be seen as a p-order conic programs. Or I can say that instead of just having one LP norm, I have weighted sum of LP norms in the objective function. And the second stage has second stage has integer variables only. And I will assume that the elements of fj omega and t omega are integral without loss of any generality. So we said, okay, let's see what we can do with this particular problem. Can we come up with some structure or some cases where, let's say, ej omega and w omega are network flow matrices, or ej omega is a vector of all ones and w omega is a totally unimodular matrix, or ej omega are totally unimodular matrix and w omega are just identity or zero vector. So can there be some of these conditions where we can kind of convexify this set, which means can we relax the integrality restrictions on the second stage integer variable? So this, along with another PhD student, led to this work. These conic mixed integer rounding inequality for this set, and showcase that by adding these conic mixed integer rounding inequality, or CMIR, we can obtain convex hull of this set, which is denoted by S11. One is because it has only one constraint, and the other one is because it has only one integer variable in that constraint. So the plan was, okay, let's see, can we do some extension of S11? Yeah, so this is... So first plan was, let's look at some multi-constraint generalization of S11, which means that we will look at this set, the RMK, which has M constraint, where each constraint has a same integer variable, sigma k, and a continuous variable, a non-negative continuous variable, rho ki. Okay, so you have this multi-constraint generalization of set S11. Now, can we have the n integer generalization of set RMK on the same lines we had for continuous multimixing set, which means, how about instead of having only one integer variable in each constraint, we have multiple integer variables in each constraint in each of these L1 norm or conic polyhedral constraints, also referred to as. And we have n integer variables in this set. So we denote it by SMNK, where M is the number of polyhedral conic constraints, N is the number of integer variables in each of those constraints. Or if we want to take the intersection of, we define this set which is SMN capital K, which is intersection of the set SMN K, where K goes from 1 to capital K, and also taking their intersection with uh, where these integer variables are connected by these linear constraints A sigma greater than equal to B. And we denote this set by SMN capital K. And we said, okay, what can we do about this set? As we observe, corresponding to each constraint, we can use conic MIR cut generation procedure to generate an inequality, which will be valid for this set. But the question is, under what conditions those inequalities will be sufficient to provide the convex hull of this set? Okay, so with that idea, we started to derive some conditions on this matrix A and GK, which is kind of the metrics or the coefficients of the integer variables, and observe that or prove that under these conditions, if we add these MIR inequalities to the set or to the continuous relaxation of the set SMNK, we can obtain the convex hull of the set. And then the idea was, let's move this by considering a set when you are having two stochastic conic mixed integer programs where these EJ have some property, EJ and W omega have some property. So which means if W omega is a network flow matrix or EJ omega is also a network flow matrix, then for P equal to 1, we can obtain a linear programming equivalent for this set. For P greater than equal to 2, we still have valid inequalities and we are able to obtain convex approximation of the second stage feasible region. Again, for more of such set, you can refer to this paper. The whole idea is I'm just trying to give the overview and then getting into the effectiveness of these approaches. So this approach also, we call it as a convexification or the second stage convexification approach, turns out to be computationally quite effective as we were anticipating. So when we solve the problem two-stage stochastic mixed integer program instances, Cplex failed to solve 248 out of 384 instances, excuse me, within 10 hours. But by adding our cuts, we were able to solve this using decomposition approach in 19 minutes on average. Similar type of the results we observed when we were looking for conic mixed integer programs for P equal to 1. Cplex was not, Cplex with its default setting without these scenario-based conic MIR cuts took 800 seconds on average to solve the extensive formulation. But by adding the scenario-based conic MIR cuts, Cplex took 143 seconds on average and reduced the time by up to 25 times and 4.6 times on average. So just to give you a glimpse of these computational results, so each entry in this or each row is average over 5 randomly generated instances. And these are the results when no cut was added and the problem was solved using Cplex with its default setting. And these are the results after cuts were added and then it was solved using Cplex with its default setting. So I where is the number of integer variables in the problem, and if you observe that after adding cuts, the number of integer variables has dropped down drastically. But there is a cost to be paid, which is the cost is that we had to increase the number of linear constraints has increased because we had to add these large number of cuts as well. So, but overall, the time taken, which is this column, is improved comparison to this one. So here we use the Cplex Benders decomposition routine, but it was not very effective when we used it at that time. So for some instances, it is computationally efficient. For some, it is not. But overall, when we add these cuts for the extensive formulation, it is quite effective. We also saw we can add these cutting planes for distributionally robust conic mixed integer programs as well. For computational experiments, we assume that the number of distributions in the set or the ambiguity set are fixed. And we observed that Cplex was not able to solve uh, 4 out of 9 instances within a time limit of 3 hours. But after adding these cuts, Cplex solved these instances in 286 seconds, so which reduces the time taken to solve the instances by 446 times on average. Okay, so I have 5 more minutes. I won't be able to cover up a lot of stuff here. So what I discussed so far is more about how to develop cutting planes and then use off-the-shelf solver. Uh, Another way to solve the distribution robust programs is to develop decomposition algorithms uh, for solving those problems. So we have developed different algorithms depending on the type of the problem. So today I thought if I will have time to touch base on this two-stage distribution robust disjunctive programs. So a disjunctive program, it's an interesting disjunction is an or operator. So when we say that this inequality is to be satisfied, this inequality is to be satisfied, it's an and operator that both constraints are to be satisfied. When we say disjunction, either this inequality is to be satisfied or this inequality is to be satisfied. It's a disjunction. So which means that I'm looking for set. So here, if I have this disjunction denoted by this big V, it is saying that either X will satisfy this set of constraints for a given S, or it will satisfy another set of constraints. You can end up having two different polytopes which are not connected at all, which makes it a non-convex feasible region. So similar type of disjunctive constraints we added in the second stage problem as well, and thought that we can we solve these problems. So in deterministic setting, this problem has been studied. So this is how here is this small example of this problem. So here you have these disjunction, which means that x1 bar and x2 bar can satisfy either this constraint or this constraint. Similarly, in the second stage, either this constraint will be satisfied or this constraint will be satisfied, and this constraint has to be satisfied. It's with and. Now, if we just observe it geometrically, this example, the second state feasible region. So we want to just observe what will happen to this second state feasible region, 7B to 7D. If I pick X is 0, 0, 0, and I pick a scenario omega 3, this is how the feasible region will look like. Okay, it's a non-convex region. Now, if I pick different X but keep the same scenario, the feasible region has changed, which is this triangle and this dot here, or this point here. If I keep X to be same and change the scenario, the feasible region has changed. Now, interesting thing to observe here is if I derive an inequality for this C, right, something like this, if I try to obtain the convex hull of this set, it might not be valid for this one because it will kind of pass something like this. It will cut off the feasible region. So that's what I was referring to add some of the globally valid parametric inequality. For how to generate them and to solve them. Again, the motivation is it goes back to Egon Balazs's his biography, which is completely separate from his, but it was a fascinating one. Like I would recommend to read it, and some of his work in the deterministic setup. And since the disjunctive programs they subsume binary problems, so we said let's look at how to solve two-stage stochastic, two-stage distributionally robust disjunctive programs. I won't. So two key things. So I'll touch base on. So two key things. So what we did for the first stage was we used a typical reformulation technique for the disjunctive programs to obtain binary variables, only binary variables in the first stage. And for the second stage, we used the convexified, or so Balazs has provided a convex hull description of disjunctive programs and some classes of inequalities for solving the disjunctive programs. So we use those two frameworks in the two-stage setup. Note that we have some aspect which is the presence of this X. So Second stage is dependent on X, so we had to take care of that business. But I won't be having much time to get into this. I'll just share the result up here. Is so the algorithm that we provided, it converges in finite iteration, and it works for different. It's ambiguity set agnostic, which is independent of what type of ambiguity set that is to be picked up. So an ambiguity set can be defined either by, like I mentioned, by taking bounds on its mean, its variance, third moment, fourth moment. So essentially, if you have finite sample space, uh, even if it is not finite sample space, it can be defined in that way. Uh, there's another framework called as Kantorovich set, which is I have a reference distribution and I'm looking at set of all distributions which is at epsilon distance from that reference distribution. So the algorithm that we provided is applicable to varieties of the ambiguity set. Uh, so I'll conclude at this point. So we discussed about continuous multi-mixing sets, some facets. We're not able to go to the extended. These are some generalizations of continuous, and we also touched base on some generalization of continuous multi-mixing set. The cut generation procedure generalizes various existing cut generation procedures, and we observe that the cuts are quite effective for multi-module capacitated lot sizing problems. We discussed about conditions under which the integrality restrictions on the second stage integer variables can be relaxed. And the plan was to discuss decomposition algorithms for solving two-stage distributionally robust disjunctive programs with general ambiguity set. With that, I'll stop here so I'll keep the remaining time for Q&A. And thank you again for the invitation.